When you hear the term software quality, what's the first thing that pops into your head? For most of us, it's testing, right? Running a program, clicking all the buttons, basically just trying to break it. But what if I told you that's only one small piece of a much bigger puzzle? That the best engineering teams use a whole toolkit of techniques, long before a single line of code is ever executed. Okay, let's dive into what that toolkit looks like.
I mean, we've all been there. The app that crashes for no reason. The website where a button just does nothing. Software defects or bugs are just a universal part of life. They're frustrating, they can be super costly, and the whole point of a good engineering team is to find and squash them before they ever get to you. So today, we're opening up the Professionals Toolkit to see exactly how they do it.
And for this explainer, we're not just making this up. We're drawing directly from the source. The insights we're about to cover come straight from a software quality engineering lecture by Assistant Professor Abdul-Rahman Mahmood. He's an IT and cybersecurity consultant and also the author of the AlphaPaler cryptographic tool, which, by the way, is officially used in certified ethical hacking labs and distributed with Dr. William Stalling's famous textbook, Cryptography and Network Security. So yeah, we're in good hands.
So here's our game plan. First, we're going to look at the simplest, most fundamental methods, basically getting a second pair of eyes on the work. Then we'll level up to more formal, structured inspections. After that, we'll bring out the big guns, the real power tools of quality assurance. And finally, we'll put them all side by side to figure out how you choose the right tool for the right job.
All right, let's start at the beginning, with the most fundamental and, honestly, the most human way to find problems. These are the techniques that are all about simple review and collaboration. Think of them as our very first line of defense against those obvious, facepalm-worthy mistakes.
The very first tool in the box is the desk check, and it's exactly what it sounds like. It's like proofreading your own essay before you hand it in. You're not running any code, you're not doing anything fancy. You're just sitting at your desk, reading through your own design, your own logic, and looking for those conceptual mistakes or things that just don't quite add up. It's simple, but you'd be amazed what you can catch.
Okay, next up is the review. It's a lot like a desk check, but with one critical difference. You're looking at someone else's work. And this is huge, because a fresh pair of eyes can spot things the original author is completely blind to. They're too close to the problem. Different experiences, different perspectives, that's the secret weapon of a good review.
Now, the walkthrough takes things a step further. This is a bit more organized. Here, the author actually leads a group of people through their work, explaining their thought process, their design choices, why they did what they did. The goal isn't really to hunt for typos, but to check the overall soundness of the logic. Does the big picture actually make sense? It's basically a collaborative sanity check.
So let's boil it down. The desk check is you, inside your own head, checking your own logic. The review is bringing in an outsider, someone who can see the forest when you're stuck looking at the individual trees. Both are absolutely essential. But what happens when the stakes are higher and just an informal glance isn't going to cut it?
Well, that's when we move from informal chats to really structured, formal processes. These are the techniques you pull out when things have to be right, and you need a systematic, repeatable way to find defects. This is where quality assurance really gets serious.
Look, an informal review is great, but it can be inconsistent. To really guarantee quality, you need a formal process, a defined set of steps, defined roles, something that ensures every piece of work gets the exact same level of scrutiny. And that's where powerful methods like the Gilb inspection come into play.
The Gilb inspection process is incredibly structured. It starts with planning and a kickoff. Then everybody checks the document on their own before they all get together for a logging meeting where defects are officially recorded. But here's the absolute genius part. Step 5B, process brainstorming. The team doesn't just fix the bug, they stop and ask, wait, why did this bug happen in the first place? And how can we change our process so this never happens again? See, it's about fixing the system, not just the symptom.
All right, time to bring out the heavy hitters. These are the most advanced, most specialized tools in our quality toolkit, and they represent two fundamentally different philosophies for how to achieve nearly perfect software.
Think of it like this. On one side, you have formal verification. This is the mathematician's approach. The goal here is to mathematically prove that the software is 100% correct. Then, on the other side, you have fault tolerance. That's the engineer's approach. This one assumes failures are going to happen, and it's all about designing a system that can handle them gracefully without a catastrophic crash. Let's dig into each one.
So, formal verification is, well, it's intense. You have to create a super precise mathematical description of exactly what the software is supposed to do. Then, you use formal logic, like a mathematical proof, to demonstrate that your code meets that specification under every possible condition. It's incredibly powerful, but also very difficult and expensive. That's why you usually only see it used for the most critical systems, like flight controls or medical devices.
Fault tolerance, on the other hand, is all about resilience. It's the opposite philosophy. Think about a big airplane. It has multiple engines, right? If one engine fails, the others can keep the plane flying. That is fault tolerance. It's not about trying to be perfect. It's about building a system that can take a punch and keep on going, making sure a small, local problem doesn't bring down the whole system.
So we have this whole toolkit now. Informal reviews, formal inspections, mathematical proofs, and these super resilient designs. How in the world do we choose which one to use? Well, in this final section, we're going to put them head-to-head to really understand their unique strengths and weaknesses. Okay, first, let's ask a really basic question. In engineering, we actually distinguish between 3 stages of a bug. An error is the mistake a human makes. A fault is the bug that ends up in the code because of that mistake. And a failure is when you, the user, see the program crash or do the wrong thing. So how do our tools deal with these different stages?
And this table just lays it all out beautifully. Check it out. Inspections and formal verification are amazing because they find the errors and faults directly, before the program is even run. They catch the problem at the source. Testing is totally different. It works backwards. It sees a failure, a crash, and then you have to work your way back to find the fault that caused it. And fault tolerance, it doesn't find defects at all. It's designed to handle faults and failures so you never even notice them.
Okay, so they all work differently. That must mean they're better suited for different kinds of problems, right? You bet.
Now this, right here, is one of the most important distinctions in all of software engineering. Inspection is a static examination. You're just reading the code, not running it. This makes it amazing for finding logical problems that are self-contained. Testing, on the other hand, is dynamic. You're actually running the code. This makes it essential for finding problems that only pop up when different parts of the system start talking to each other.
And this final table really puts it all together. With an inspection, the result is easy to understand. You see the bug right there in the code. With testing, a result might just be a crash log, which can be really hard to decipher, and formal verification is the hardest of all. So, you pick inspection for static logic, testing for dynamic interactions, formal verification for when you need absolute mathematical certainty, and fault tolerance for systems that simply cannot be allowed to fail.
So, here's the big takeaway. There is no single best way to ensure software quality. It's a total myth. A great team doesn't just use a hammer for every job. They use desk checks and walkthroughs for the simple stuff. They use formal inspections for the critical parts. They use dynamic testing to see how it all works together. The best strategy is to have a full, diverse toolkit and to know exactly which tool to pull out for which problem.
And that leaves us with a pretty fascinating thought for the future. You know, for decades, we've been developing these very human-centric tools to check human-written code. But as AI begins to write more and more of its own software, are these tools even going to work? I mean, how do you perform a desk check on the logic of a giant neural network? That's a challenge we're all going to be facing very, very soon.